So let me share. Oh yeah, and then our focus today will be about extended command filter because EKF is the most used command filter. So the basic idea of EKF is that you are linearize the system, meaning that if you have a vector of state space vector, and then you calculate and then you want to linearize, then what you need to do is you need to calculate the Jacobian matrix of the system, and then you replace the uh, transition matrix with the Jacobian. So I will share my screen just to make it clear. So I don't prepare any particular notes, but we are going to discuss it later. I just prepare one short note, but it's about modeling. So last week, I hope you are familiar with the command filter. So basically, command filter is a method to estimate the state, given that our model has some degree of uncertainty or noise, and also the sensor has noise. So this is a general formulation basically. So let's say that we have discrete time state space model, which can be written as xk equal to fk times xk minus 1 plus b. This is the control terms. This is the f. In this case, f is the state transition model, and then this w is the source of uncertainty. Usually we assume that for command filter, we assume that this wk is Gaussian with known covariance. So it looks like this. So this w is a Gaussian, and for normal distribution or Gaussian distribution with zero means, and you also know the covariance. In this case is qk. And then for the measurement, we assume also that this measurement is corrupted by this noise vk. And again, this noise has to be Gaussian, white noise with known covariance R, and also zero mean. So this is a typical problem that can be addressed by command filter. We see this as a stochastic, discrete time stochastic system. It's stochastic because we have an uncertainty here, and also at the measurement. So command filter itself was derived for this kind of system, which is linear. And if the system is linear, the command filter is the optimal state estimator, meaning that command filter is the best estimate that you can get. What we mean with the best estimate, it means that the estimate minimize the distance between the estimate and the method minimize the distance between its estimate and the actual data. And then command filter basically a set of algorithm. It consists of two steps. The first one is predict. So when you try to predict, meaning that you haven't used your measurement, therefore it's called a priori. So in this case, you basically run your model. So this is your model, and then you can get a priori state estimate. So priori state estimate is you obtain only for the model from the model without having any data input. While in the second step, it is update. Basically, if you look into this equation, update a posteriori state estimate. Posteriori meaning that you incorporate your data. You can see here that basically this is your priori, this is from your model, plus some gain, this is called Kalman gain, times what is y tilde, y tilde is the difference between your measurement and your model. So this is your measurement, zk, and this is your model. And this Kalman gain try to minimize this y tilde. So the Kalman gain is chosen by this algorithm such that it minimizes the difference between zk and this guy. This is from your model. Okay. And then this guy is basically, the Kalman gain is basically can be calculated using this formula where S is this one, innovation covariance, and then P is quite important. What is P? P is basically an error covariance matrix. And then how to choose this initial P? That is something that it's depend on your knowledge on the earlier initial estimate. So if you are sure that your initial estimate quite close to the actual data, then you can choose small pk p0, sorry, small initial covariance matrix. But if you are not sure that if this close or far, then you can put a big number, maybe 100, maybe 1000. We will see that later when Adam give you some example. So in this, if you want to run the Kalman filter, first of all, you need to initialize, of course. You need to initialize the state, this K, and then you need to initialize this P, matrix covariance error covariance matrix P. And yeah, I mentioned to you how to choose this P. And then you need to also define what is Q and what is RK. So in real world, I think I mentioned also last week, if you buy a sensor, sometimes the manufacturer will give you the standard deviation or accuracy of the sensor. So basically, this RK can be calculated from the standard deviation. While QK you can set as 0, for example, if you are sure that your model is perfect. But if not, you can just put some small number for this QK. But in practice, you could also think that this QK and RK can be considered as tuning parameter, meaning that you change the value of Q and R at the beginning, such that you can minimize by calculating the root mean square between the estimate and the actual data. So what I'm going to do now is what I'm going to do today. I will give you 2 examples. The first one we will discuss with about estimating coronavirus basic reproduction number. And the second one, since and the reason why I give you this, because I would like to show you the application of Kalman filter not only on robotics but also later with Adam he will discuss about this application of Kalman filter in robotics. So that is what we are going to do today. The first part with me, we are going to learn how to implement Kalman filter for estimating COVID-19 reproduction number. While with Adam, you will learn about how to implement it in robotics. Okay, so that's what we are going to do today. And then the similarity between COVID-19 and robots is that the system can be described by nonlinear equation or nonlinear system. So what is different in here is that when you have nonlinearity, you can linearize the system, and then you can replace this F, this transition matrix, state transition, by the Jacobian matrix. So if you look into the extended computer, it's called extended computer. What happened in extended computer is that when your system is nonlinear like this, so this nonlinear, and also you have nonlinear measurement, you calculate the Jacobian like this. I guess you are familiar how to calculate Jacobian from previous lecture. And then you once you get your Jacobian, you replace the state transition matrix with this Jacobian. And that's it. That is the idea of the extended computer. It's quite simple. It's quite straightforward. What you need to do is just calculate your Jacobian matrix and then replace the state transition matrix with this Jacobian. Okay, do you have any question? Is it clear?
Yes, it's clear.
And I think for from last week, I also give you some codes on how to use Kalman filter for cruise control system, for example. And you can see in the code that it's quite straightforward to implement. What you need to do is to define the update, the predict. How to, there are two steps to predict. Predict is the first one, and the second one is to update your covariance matrix. So it's quite straightforward. Okay. Now what we are going to do is I made one small note. Actually, I already put this in the eLearn. You can also download this. But this is about estimation of COVID-19 reproduction number. So what is reproduction number? Reproduction number is, if you think about if we have one couple and then they have one child, then it's mean that the reproduction number is 1. If they have two child, then the reproduction number is 2. If they have 3, reproduction number is 3. But we can observe that if this couple and the other couple has the average, or in the population, each couple has reproduction number equal to 2, then the population more or less would be constant, right? But if the reproduction number is 1, for example, each couple has only one child, then the population will shrink and it will extinct. But if each couple has reproduction number larger than 2, let's say 3, then the population will growing. So the reproduction number of virus also quite similar, except that in order to reproduce, what we mean with reproduction is that one infected person, for example, if this person infect to other person, it means that the reproduction number is equal to 2. If in average, in one population, if the average of infected person infects 3 other, then reproduction number equal to 3. So that's quite simple measure. So, but the difference is that this reproduction number should be less than 1 if you want the disease will disappear. If the reproduction number greater than 1, then we'll have epidemic or pandemic. So that is the idea of this reproduction number, basically. And then now what we are going to do is how to calculate this reproduction number, given that we have a large population. So we want to calculate the average of this reproduction number. So in epidemic theory, basically, I just learned this last month, since the beginning of coronavirus. So there is one model that people usually use for prediction or estimation. It's called the compartment model. So basically, in one population, let's say that the population has n number of people, we can divide this population into compartment. The first compartment is susceptible. This is a healthy population. This healthy population has a probability that can be infected into infectious population. So the red one, this is the sick people. So this is healthy people, and this is sick people. And then we know that the characteristic of virus is that either you can have like vaccine, or if vaccine is not available, like right now, what happened with coronavirus is that after some days, after you have incubation period is basically a period between you get the virus until you show the symptom. So that is in incubation period. And then you have infectious period or infectious time, that is between basically what I read is that 3 days after you contact the virus until 9 days. 9 days is the average or the mean. And then we will have an outcome. Either you are recover or you are dead. So that's what happened now. Okay, so there are you can make a lot of compartment. Actually, this is the simplest one: susceptible, infectious, and recover. But you could also make another compartment. Let's say D for dead. Now, this also has several parameters. For example, that this beta is a contact number. So the average contact number. For example, if one person maybe in one day has, let's say, 12 contacts, and then what is beta is actually equal to this number of contacts times the probability that this person can be infected, times some period of time, because this contact is defined from for some period of time. But basically, this is time varying, of course. It depends on the behavior of society. If we are not aware that the virus already in society, then beta will be quite large. But once we have social distancing or physical distancing, then this beta will go down. And this gamma is recovery rate, and sometimes we could also define death rate, or case fatality ratio. But basically we can put this kind of formulation into state space model. So it looks like this. What is S? S is the number of healthy people that has probability to be sick. So S is the number of healthy people. And then usually at the beginning, the number of healthy people is also equal to N. So it's equal to the number of population. So S depends on T. depend on time. And then we also have I. This is the number of 6 people, or we usually call this as active cases, number of active cases. And then we have R. This is the total or the cumulative number of people that recover, and D is the cumulative number of people that die. So this is one of the simplest model that we can get. And then on the right hand side, you see that we have multiplication between I and S, meaning that this model is nonlinear. Okay, so we have nonlinear model, and then the reproduction number is basically defined like this. So it's equal to beta divided by gamma time plus kappa. And then this gamma and kappa is usually known. So it's equal to 1 minus, this gamma equal to 1 minus case fatality rate. And this is known from data divided by TI. So TI is called infectious time. And this is something that you need to measure from clinical data. For COVID-19, this infectious time is about 9 days with standard deviation of 1 day, meaning that the infectious time is between 8 to 10 days. Okay. So if we go back into this equation, so basically we have 3 parameters: beta, gamma, and kappa. But then actually it's only depend on beta and times in infection times, because infection times can be used to calculate this gamma and kappa. So there are only 2 parameters, beta and infectious time. So until this, do you have any question? Was it clear?
Yes.
Yeah. How about the other?
Yes, clear.
Yeah.
Clear, right? So you have a state space model with 4 state, and then if you look into these parameters, you actually only have 2 parameters, and that is beta and the infectious time. Okay, because infectious time is once you get infectious time, then you can get gamma and kappa. Okay. So actually, there are a lot of variants of this compartment model. This is the simplest, as you divide into 4 compartments: susceptible, infectious, recovered, and death, basically. So, but sometimes you can also have like people that is exposed. So you have between S and I, you have exposed. So basically, exposed people is, I mean, if we think about country like Japan, for example. So country like Japan, they have different islands. So if one person got infected in one island, then the exposed is only in the island, and in that island, while in another island could be considered as, I mean, the whole country could be considered as suspectable, but only in one island that is exposed, for example. So you can have another compartment here. But in a country like Denmark, for example, we can assume that all people are susceptible, meaning that we don't care about this exposed. We assume that everybody will be exposed. And sometimes also you can make a quarantine compartment, meaning that once you get infectious and then you can just quarantine these people. So you can make another compartment here. The reason why I use this shared model with four state is because we have data of number of active cases. We have data of number of how many people who recovered, and we also have data about number of people who are die. So if I look into, I usually use this as my main source. Let's say where is Denmark? How many people seen this this page before?
Yes.
You have seen this before. So you see this, that we have a number of active cases. Basically, this is I. This is data of I. And then what happened in here, I think if you look into this data, this is the green one. This is the number of people who recover. So we have R. We have data of R. What happened in here is that at first we have 0 recovery, and then suddenly we have almost 900, meaning that maybe there are a lot of people who already recovered, but then the government just record in one day here. So we have this spike basically like this. But another country usually quite smooth, but that's fine. So we have this type of data. Now, the problem is that we have data of I, we have data of R, we have data of D, the death, and then how about S? S basically is the remaining people who are in Denmark, meaning that it's equal to N, the number of population, minus the number of people who are sick, minus the number of people who are recovered, minus the number of people who are die. So meaning that you could also have this information. So you have information about S, information about I, R, and D. So you have all of the information, but now the problem is that you want to estimate this R. This is what we want to estimate, the number of the reproduction number at time t. Remember that this beta is actually a function of time. Okay, so this beta is function of time also. So this is kind of not state estimation, but parameter estimation. Meaning that you want to estimate the parameters from state space model. So gamma and kappa is constant, both are constant. Meaning that beta equal to RT times gamma plus kappa. So I can just replace, I can substitute this beta. I substitute this beta with gamma plus kappa times RT. I think that makes sense, right? Meaning that now you will have a problem of estimating RT. So you have RT over here. So I hope now you are understand with the problem. You have state space, and then you can measure all of the state, but the state space depends on one parameter, and then you want to estimate this parameter. So this is parameter estimation problem, not state estimation. So how to solve this problem? It's quite easy actually, by using some tricks. And you just keep in mind that this parameter RT is depend on T, right? But then we can assume that this RT, the reproduction number, is piecewise constant function, meaning that if you think about the stair, so it's just like constant, and then it will have jump, and then it will constant again, it will have another jump, and then it will be constant again. So we assume that this number, okay. So now we have beta, but then I substitute beta with RT times gamma plus kappa. So means that so means that now the equation has only one parameter that you want to estimate, and that is RT. So beta is function of RT via this and then I assume that this RT is piecewise continuous, piecewise constant, like stair. So, and it will be changed every day. So let's say that, for example, today RT is 1.1, tomorrow it will be 1.2, the next day it will be 1, so it will be like stair function. So what happened if I and then if I have this piecewise constant function, if I take the derivative of this piecewise constant function, what is the derivative of this piecewise constant function? Anybody? What is the derivative of piecewise constant function? Yeah, basically it's 0, unless at the, when it jumps. When it jumps, then the derivative will be equal to Dirac. Actually, Dirac delta function. It's not, I mean, infinity if we're talking about classical mathematics, but Dirac actually, this physicist, he defined what we call as distribution theory. And then based on this distribution theory, when we have jump, like in stair function, then the derivative will equal to the Dirac delta function. But we won't go into that area, but we only assume that the derivative of this piecewise constant function is equal to 0. Okay. So since the derivative of this piecewise constant function equal to 0, means that RT dot. So I made another state here, RT dot. I didn't put it here, but you can think about RT dot is equal to 0. Okay. So I made the fifth state. So I consider the RT as a fifth state. And the fifth state is that RT dot equal to 0. If I discretize this using Euler discretization, I will end up with this kind of model. So you can do the math. That is quite straightforward actually. So the fifth equation, this RT dot equal to 0 becomes RTK plus 1 equal to RTK, meaning that this RT is constant. Okay, and then the fourth, for example, this is originally d dot equal to kappa times I. So it's become dk plus 1 because d dot is actually dk plus 1 minus dk divided by delta t. Now it's become like this. R also the same. R dot equal to gamma times I, but then you discretize between become R dot become Rk plus 1 minus Rk divided by delta t. So you have this one. And then you also could, you can do also some math, and then you will end up with this kind of model. Okay. You can do it by exercise, by doing some exercise. Do you have any question? I hope it's clear. So basically, the idea is that you have state space. There is non-linear state space, and then you want to estimate one parameters. And then you assume that this parameters is constant, meaning that the derivative of this parameter with respect to time is equal to 0, and then you consider this parameter as a new state. So you consider this parameter as a new state, the fifth state, and then you discretize, and then you will end up with this kind of system. I hope it's clear. Do you have any question? No? Okay. Now we have discrete time system. And then from here, you can apply what we already learned last week, and that is about Kalman filter. So I already made the codes. We will go one by one through the codes. So basically, this is the codes. Let me check it. Let me. Oh, I think I already changed some. Yeah, let's use it, this one. Oh, my mistake. Sorry. Yeah. So just run this program, and then we will go to the codes line by line. So we will start with the result. So, and this is the result. So figure 1, you can run it also yourself. So what is figure 1? So figure 1 is the data between what is estimated and what is reported. The red dot, this is what is reported, and the blue one, that is estimated from the Kalman filter. This is active case. This is I, number of six people. Six people is the number of people that recovered, and this number of people that die. As you can see here, that the estimate able to track the number of reported cases quite accurate. It's not really accurate actually if we make it, if we look into here, for example. Looks accurate, but you can see here that there is some difference. So this is the actual number, 131, 1,312, but we estimate 1,311. So there is some only one person. That is the error, but it's quite accurate. The second figure, this is what we estimate from using Kalman filter. So this is the basic the reproduction number. Now we are here at 29th of April. This is until yesterday actually, but the reproduction number up until this point is below 1, so it's quite under control. So it's fine. So how these algorithms work is basically like this. So first I need to define the data, and this data is basically obtained. You can find it from website, but the idea is that you need to record sorry, this is actually the date. This is not month, but this is the date. So for example, here from 15th of February. So this is the date, this is the month, 15 February. Here we have 0 cases. The first cases is on 27th of February. There is 1 reported cases. And then this is the basically 5,700,000. This is the Danish population. So we assume that all people is susceptible. Sorry, not suspected, susceptible. And then when we have 1 person who move from susceptible compartment to another compartment, which is the active cases or infected cases, then it will become, we have less 1 people here, and then so on and so forth. So this one you can get from this data, you can get from internet. This is also number of recover. You can see here that there is a suddenly jump from 1 person, and then the government report at the 1st of April that almost 900 people recovered suddenly. But the government also record the number of people that died here. And then actually one assumption in compartment model is that the number of people is remain constant, meaning that we have the third, this columns, if you add this column, it will equal to number of people who got coronavirus, because this is the active cases, this is the outcome, either recover or death. So this one will be equal to the number of population minus the summation of these 3. Okay. So but basically this data you can get it from internet. So I got it until yesterday, 28th of April. So, and then this become your input. So you have this one. And then you also need to define the infectious time, as I mentioned before, that the parameters of this one, gamma and kappa, the recovery rate and death rate depends on the infectious time. And then I got this infectious time from one journal. It's quite reliable with the standard deviation of 1. So it could goes up until 10 days, or it could go down until from 8 days. So that is the range. And then we will calculate this range below. And then this is some data that I would need. So basically, for example, like here, the CFR rate, the case fatality rate, is basically the number of deaths minus the number of cases. So divided by the number of how many people that are infected by coronavirus virus. And it's become case fatality rate. You can use this case fatality rate to calculate also this gamma and kappa. But basically, you can obtain this parameter quite easy. And then what is this data matrix? Basically, this is the C matrix. You remember that when you have measurement, you have Y equal to C times X. So this is the C matrix. And why the structure is like this is because we have 5 states now. So we have 5 states, 1, 2, 3, 4, 5. But we only able to measure the first 4, S, I, R, D. Okay. Therefore, we write it like this. We don't have the last row. And because the last row is something that we want to estimate. So this we want to estimate, and this is that we can measure. And then how about this Q and QF and RF? So I mentioned before that if we know, or if the manufacturer gives you some degree of some information about the accuracy of the sensor, you can use it. But in most cases, you use this as a tuning parameter. Therefore, here I just write some number and then try to tuning this number manually, such that the root mean square of my of error between the actual data and estimated data is quite small. So this is something that I just put it some number and then see the root mean square. It will be, I will give this below also. And then I start this simulation. Basically, I need to define the, this for initialization. And then here, this is the data. This is data from this one, basically. This is the data of the actual data, the reported data. And then I use model to predict. So this is the data, the actual one, and this is the model from the model. And then I calculate the Jacobian because the system is nonlinear. So once again, this is nonlinear system because we have multiplication, for example, here, RT times I times S. So this is nonlinear. So I calculate the Jacobian. I think in this paper, actually, I also give you the Jacobian matrix. You can see it later. So basically, this is the Jacobian matrix. And then I use this Jacobian matrix to replace the state transition matrix. So if you have linear system, then this is a state transition. But if you have nonlinear system, you replace the state transition with Jacobian matrix. And then the remaining of this is just like standard Kalman filter, basically. So like how to calculate the Kalman gain, how to calculate this x hat, and x hat equal to x. This is priori, which you calculate from your model, and this is your posteriori because you add your measurement. And then sometimes you could also make some tricks because to make sure that this reproduction number is positive. So you can use this command. Do you have any question? It's quite maybe it's quite new for some of you, but the idea, I hope you get the idea. And the idea is that you have this pandemic, and then if you want to model this, you can model this pandemic using this compartment model. But then in this compartment model, you have this data of S, you have data of I, you have data of R, and also you have data of D. What you want to know is that the parameters of this model, and that is the reproduction number, RT. You have this algebraic equation, and then you substitute into this equation. So you have time varying parameters, and then when you want to solve, when you want to estimate this time varying parameter, you do this trick. You consider it as constant, therefore you have the fifth state space representation, and then you use standard Kalman filter. Okay, so that is the simple idea of how to calculate the reproduction number. Any question? Is it clear? Or unclear at all? Hello?
It's okay. It's clear.
It's okay. It's clear. But the idea is it's quite simple. So basically, you think about nonlinear system like x dot equal to f, where f is nonlinear function, and then you have these parameters also, and then if you want to estimate the parameters, you can do it this trick basically. Yeah, Andres?
Yeah, so you mentioned that RT differentiated would when the measurement jumps, it would be Dirac delta, right?
Yes.
Yeah. How do you take this into account, or do you just neglect it?
We neglect it.
Okay.
Yeah, just to simplify the problem.
Yeah.
But in theory, it would be equal to the Dirac delta function. I think I can find some information. Distribution mathematics. This distribution theory is devised by, I think, Dirac. Yeah, Dirac delta function. The step function usually called Heaviside. Heaviside function. And then what is the derivative of this? Yeah, this one. So H, this is the Heaviside function. Heaviside is basically this guy, the step function like this. Step function. And then the derivative of step function is Dirac delta function. Okay. Dirac delta function is basically a function that zero everywhere except at this point it's infinity. So that is the definition of Dirac delta function. You could also write it like this. If it is in physics, so you have force, for example. Yeah. But in many engineering problem in robotics, for example, the parameters is usually constant, and you want to estimate this constant parameter. So you don't need to think about the delta Dirac function. But since we want to estimate, since our understanding is that this RT will be changed over time, then we need to make this assumption that RT is a piecewise constant function. Okay, so that is the trick.
Yeah.
Any other question? Otherwise, I think actually that's it. What I want to discuss with you. After this, you will have one session with Adam, and it will be about how to estimate the state using Kalman filter. So I will just give me a second. Yeah. So this is the problem. You have a single-link flexible joint robot. Like this, single-link flexible joint robot system with 4 states. This theta theta is the angle of rotation of the motors and link. So this is the angle of rotation of the motor. This omega is angle of rotation of the link. This is the M for motors and L for the link. So theta is the angular velocity. Theta is the angle of rotation, while omega. Where is the omega? Yeah, the omega, which is actually theta dot, are the angle of the velocity. Okay, so you can see here that we define omega as theta dot. Okay, so this is a system of 4 states, and then what you will discuss with Adam is that let's say that we only have 2 states that can be measured. Let's say the first one and the second one. What happened if we only have 1 state that can be measured? Are we able to reconstruct the other state using Kalman filter? So that is what you will discuss with Adam. And the basic idea is just to use extended Kalman filter. So you will need to calculate Jacobian. You can use the programs from last week for, let's say, for the Cruise control system, but then you can define this as the input. So this F, this F is basically the state transition matrix in continuous time. When you discretize, you will get this A. A is new discretized transition matrix, which is equal to identity matrix plus the state. This delta is the time step times F. Okay, so but I think Adam will discuss this further with you. Adam?
Yes, can you hear me?
Yeah, are you ready? So
Yeah,
I will finish this lecture,
sure.
and then you can take care from there.
Sure.
Adam also will share with you the code, so I hope you also will try to understand what happened when we want to estimate the state using Kalman filter. Okay, so see you next week then.
Yes.
See you.
Yeah, see you.
Hi, can you hear me?
Yes. Yes.
So, do you have the paper that Agus was speaking about? No? I will send it in the chat. Just a sec. So it's this one, and you can go directly on the page 391. So if you go on the page 391, everybody's there. Yes, no, maybe?
Yes.
Okay. So
Yeah.
this is just the description of the dynamics of the elastic robot that I was speaking about. And I would just suggest that you try to read it, just the application section, until it ends with implementing the observer that we don't need to use the command filter. So just the page 391 from for application app. If you have any question, just ask, and then we will try to implement it together in MATLAB. Does this sound reasonable?
Yeah, sounds good. Yep.
Yep.
So just a little background, I don't think I would said it. This is, those are the two angles for elastic robot. Have you ever heard about an elastic robot? Do you know what it is? That's a no, I guess. Okay, so basically elastic robots were used mostly in space exploration, and they were very involved in the 90s. I don't think they were actually used. So that was the basic idea. The thing is that you have a spring and a motor that loads the spring, and then it just loads the spring so it can jump from one side to the other. And you are in this very thin atmosphere, celestial bodies with very low gravity. So basically with just little thrust, you can go very far, so you can collect data and so on. But I don't think they were actually used. And if you look, the paper is from 97. It's referring another paper from 94. I can send you the schematic of the robot I checked before. So it looks like this. So you see that there is the DC motor and the spring that's being loaded. And you get the two angles as the input that we have in the system, and then it just loads the spring. Have you ever seen an elastic robot? Okay, I can show you one. My ex-supervisor was working on those in the 90s. it looks like this. This one is slightly more complex. You see that you have the two springs. And then in this fancy mechanism, because when it jumps, it needs to land on a specific location so it can jump again.
When we have read it, what were we supposed to do?
So basically, we are supposed to implement this in MATLAB. And
Okay.
I am not sure what formulas Agus used, because the few things that I saw while he was speaking was the formula from Wikipedia that I don't find very useful. If you want, in the book, the one that Agus sent you the last time, on page 409, there is exactly the procedure. Page 409. And I would just start using the same code as we done the last time, and I'll give you some initial data. So when you open it, you will need final time and the DT, and the initial guess as well. So let me know where you're there. Just sent you a link to the hopping robot that I was speaking about. So the elastic robot.
Are we just supposed to implement the extended Kalman filter ourselves, or were we going to do it together?
We can do it together. That's fine with me.
Yeah.
I don't know. Do you want to try to share the screen?
Yeah, I'll just open MATLAB quickly. Okay, I think I'm sharing it now.
Okay, I can see.
Yeah, so it's just the one from last time.
Okay.
I have opened.
So instead of DT, no, DT is fine, but final time I have 6. Yes.
For what you said?
Well, final time 6, TF equal to 6.
Yeah.
So we go from 0 to 6 with that step. And then you just have to define the system description from the papers. So just rewrite F, C, and D matrices.
Yeah.
As they are in the paper.
Okay.
Okay, now you have to discretize it. Make sure the paper was very nice because it wrote you the formula how to do that. So yeah, exactly there, where A equal to identity plus delta F.
So identity, where do you see that?
So if you go
okay, there. Yeah.
Exactly.
The G also. Okay, so F3.
Okay, so now you need the X hat. So your initialization basically. And I tried it before. They don't tell what initial gets used in the paper in phase of reproduction in science, but I tried this one and it worked.
Okay.
Then you have to define the control.
Yeah.
And my control was 0.1. So U equal to 0.1.
Okay.
And that's it. Let's check in the iteration. Let us see what happened there. Yep.
Okay, so we should have A times X here, I guess. And B times U. Should we still have the noise added?
Yeah.
Okay. And then also the
But
F of X of 3.
yeah, okay.
And
Perfect.
then C right there. Okay, I guess that's it
Wait.
for this part.
So with the noise, you have 4x4 now. So we are missing one random.
What am I missing?
The noise.
The noise.
Up. Oh, there. Down.
Oh. Like that?
Yeah. Also the multiply by 100 both.
Multiply by 100.
Mm-hmm. No. I mean 0.01 by 100. So instead of using that, I would use wait, what I used. I guess I use just yeah. So it's Q1 per, yeah, exactly, but then R, so instead of 0.01, write 1, because it was too small. And the R is 4, but you need to multiply it by rank of C, because here we don't have just one value, we have two.
I couldn't hear what you just said.
You have to, yeah, sorry. I will write it down.
Okay.
Super. Yes.
Okay.
Because basically the above one is rank of A, right? And you have here rank of C. That's 4.
Okay. Yeah, okay.
Okay. Yes. Let's go back there. Yes. Actually, I don't have the square root.
Okay.
I guess the exercise was different the last time. Okay. Yes. Yeah. Also, you have two rows, right? So in the Y, the noise has to be random.
Okay.
And it's the row vector. Exactly. Okay, and now in the prediction step,
That should be A and B, and then A.
So pretty small that I can see anything.
Where's H here?
This is better.
H, okay. So, what should H be for this one?
How did you write the GX?
The GX, I wrote the f of x here.
Okay. Let me check. Yes. So that's the f of x.
Yeah.
So if you go down, yes.
Should I add the f of x here? Or
Wait. Did you go up? Just 1 second. Yeah, precisely. So just add f of x, and
okay.
it's your basically your initial guess at the first step, and then you update your initial guess. So it's f of x of and you are using x of 3. Are you sure? I'm not sure.
I'll just check.
Try to go up.
Oh, over here? In MATLAB?
Yeah, it's x hat. You see? Third one. Because then in the formula you have in the what is this? Yeah.
Oh yeah. Yeah, x hat. Okay.
Because in the formula you have that x hat plus. So the first iterate is the x0, that is defined in the initialization, and then you apply directly that one.
Okay.
Okay. Let me check the rest. Okay, so sounds good. Yeah, okay. Okay, so yeah, no way the sizes does not match. So if you go in up, in the formula, you have the fk minus 1, pk minus 1, fk minus 1 transposed, which is your f that you have defined before. So instead of using that one, use directly the g of x.
Here?
Yeah, give me a sec. Go up. Yeah, no, it's correct. Sorry. Yeah, yes, and then you need the Jacobian, right?
Yeah.
Okay. So if you go down, I will do an intermediate step to get this A, which I would call in another way. Just call it, I don't know, FAX, FX.
The A down here? Or? Okay.
So call it in another way, and
I
before
just call it J for Jacobian.
And then J equal to, and this is basically your matrix that is in the paper, and it's the matrix, the one that is in the middle between M and N.
Okay.
And we just use that one.
Okay. So let's see.
Then multiply it. Yeah.
equals to x3. Is that just it?
So let's check. Yes, precisely. But instead of do one thing. Move the last row because then it makes some operation that doesn't make that much sense to me. So move the row with cosinus to the last row. Switch the rows.
Okay.
Yeah. Okay. Correct. Yes. Yes, and you need to add a.
Add a.
Yep.
Here.
No. Yeah, you can do it there as well, but I would do it when you're defining the Jacobian. Yeah.
Okay, like that. Okay.
And you need to discretize it as well. So just multiply, not a, just the cosinus. So just multiply the cosinus by the delta.
Okay.
Okay, we are missing the square root, yes, and it's the matrix per its transpose, so it's 3.33. You need to also to multiply it by 3.33, right?
Okay, so can I do that here at the cosinus or just outside?
It's the same, yeah. You can do that as well. It's because I have no idea why to do this complex step. Probably to make it. I have no idea. But they are doing 3.33 by 3.33. If you check, and there is 0. Yeah. Okay. Yes. Looks good. Let me check. I have done this the same. Yeah, precisely. Yes.
I think you are missing a random.dt when you're multiplying it with Q. Because Q is a 4x4 matrix, and you're only multiplying it with just up above that. Yeah. I mean, aren't you missing a random?
Yeah, you are.
Yeah.
Okay. Yeah.
Okay, I'm checking the update.
Yeah.
So in the formula, you don't have sigma in this case, right?
Should I remove sigma? What did you say?
That's correct.
Okay.
You have instead of k.
Yeah.
Okay, so it uses kf, but you can leave it like this, and then you have p min, yes, by h by a little more complex stuff. So if you go on the book on page 49, I don't know, have you the book there somewhere?
Yeah, here.
Yeah, precisely. So it's 3449, last one, and it's the k that you are writing right now. So we have the min by h transposed.
Yeah. Then times the inverse of h times p min times h transposed plus m times r plus m transposed. But I don't think I have written down h anywhere.
Yeah, that's correct. That's because in your system we called it C.
Okay, C.
Yeah.
And how about M and R?
So let me check how your system looks like. Go a little up. Yeah. Okay, so that's your R.
Okay, it's just this R.
Because then you have random noise.
Yeah. How about the M?
It doesn't matter because you have random noise, so it's equally distributed.
Okay, so I should just remove the M here.
Yeah.
Okay.
Just apply the R.
That should be C and C. Okay.
Wait a sec. I'm not sure about that. Okay, CK. So if you go on the formula,
Yeah.
again, and you check the formula for x hat. So this is the x hat plus, right?
Yeah.
You have the old one.
Yeah.
Which is still x hat in your case, so you don't have to call it different names. And then you multiply it by k. Yeah, instead of x min, you called it x min? Okay. Then it works. Yes. So then you have the k multiplied by y minus c. Yes. Looks correct. Exactly. And the p plus. So basically here you don't have 1 by 1, but you have 4 by 4. So instead of that is the identity 4.
Okay. Yeah.
Yeah, and min. Okay, I'm not sure about that min. I don't have it in the formula. Yeah, no, it's done. Yeah, sure. No. Yeah. No, you are correct. Yes, go ahead.
Okay. That must be date time values.
So Life52 is complaining about the.
Try this, Emil, in your plot.
Nope.
Yeah. Yeah, this is the last part. Yeah. Okay. No, I don't think so. What it was before? Oh no. Yeah. Should still plot something. What the trace? Where is it? Okay. Data already. Hang on. Is it updated? Yes. What does the X array look like?
It's 4 by 6,000.
Okay. Makes sense. Try to plot the first one instead of the third one. Mm. Mm. Doesn't make sense. Maybe we have to. Yeah. And try to transpose it now, but I don't think. Yeah.
Yeah.
No, but if you transpose only TF, I'm not sure that.
Oh. Yeah.
Still no. Mm. Well, I can share the code video. That's easy. How is it going for the others?
I got a plot. I don't know if it's correct, but I can send it. 2 seconds.
Okay. So I just send you my code with the solution. Whoop. Yeah, it's kind of correct. You probably plotted everything.
Mikkel, what's the difference between mine and yours?
Yeah, I can't really find the difference. I have tried looking at it. You took the airplane template, right?
Yeah.
I took the cruise control. I don't know if it should be the same.
Yeah, the airplane one is called cruise control.
Yeah. Well, except we have modified the plot at the bottom. So you should just plot the X-array straight on, but you're doing that now, so...
I actually cannot see the issue as well.
Must be date time.
Huh. It's like you have defined some data type or something.
Oh my god. Okay. So it works in MATLAB 2019, but not in MATLAB 2020.
It works in my MATLAB 2020.
Oh.
Maybe just restart it.
Yeah.
It might just be a bug.
Because you're using it under Windows.
But why?
So Adam, the one who's following the blue line is the estimated and the measurements, right? And just the red ones who aren't following the blue ones are the one we are estimating.
I am not sure actually, because it's all mixed together with all the x's. If you try the solution that I just sent you,
Okay.
there are basically 4 different plots, so it's kind of easier to see. But the evolution is the same.
Sure.
Okay.
Yeah, probably should have done it quicker. Yeah. Yeah, here it converts to the solution, but if you look at the beginning, start. We'll see that it tries to mimic the solution. Especially, I guess the last one was the one that was diverging most. Try the last one instead.
Yeah. Oh yeah. I don't know why it won't let me zoom right now, but yeah, I can see. Yeah. Okay.
Okay, so that's it.
Okay. Nice. Then I guess we see you again next week.
That's correct. If you have any questions, otherwise, see you next week.
Yeah.
Yeah. Okay. Thank you.
Yeah.
Bye.
Bye.